Now we look at the negative feedback feature of an op amp. It's one of the most useful concepts in electronics, particularly in op amp applications. Negative feedback is the process whereby a portion of the output voltage on an amplifier is returned to the input with a phase angle that opposes or subtracts from the input signal. So as we can see, illustrated below, a sample of the output signal is returned by the feedback network to the inverting input of the differential amplifier. The op amp has extremely high gain and amplifies the difference in the signals applied to the inverting and non-inverting inputs. A very tiny difference in these two signals is that all of the op amp needs to produce the required output. The negative feedback is present. The non-inverting and inverting inputs are nearly identical. This concept can help you figure out what signal to expect in many op amp circuits. So take a look at the circuit there, and you can see what's going on as far as the feedback. So we can review how negative feedback works and why the inputs at the inverting and non-inverting terminals are nearly identical when negative feedback is used. Assume a 1 volt input signal is applied to the non-inverting terminal and the open loop gain of the op amp is 100,000. The amplifier responds to the voltage at its non-inverting terminal and moves the output towards saturation. Immediately, a fraction of this output is returned to the inverting terminal through the feedback path. However, if the feedback signal reaches 1 volt, there is nothing left for the op amp to amplify. Thus, the feedback signal tries but never quite successfully in matching the input signal. The gain is controlled by the amount of feedback used. When you're troubleshooting an op amp circuit with a negative feedback present, remember that the two inputs will look identical on a scope, but in fact they are slightly different. Now suppose something happens that reduces the internal gain of the op amp. This causes the output signal to drop a small amount, returning a smaller signal to the inverting input via the feedback path. This means the difference between the signals is larger than it was. The output increases, compensating for the original drop in gain. The net change in the output is so small it can hardly be measured. The main point is that any variation in the amplifier is immediately compensated for by the negative feedback, resulting in a very stable and predictable output. Okay, so there's the explanation. The next section goes into why use negative feedback. Go ahead and take a look at that. It gives you some examples here of a mathematical relationship for calculating the value Vn and AOL, the loss there, the loop. So in this case, if we had 1 millivolt and 100,000 in the gain, then we end up with 100 volts. Since the output level of the op amp can never reach 100, it's driven into saturation and the output is limited to its maximum output levels. So you can see in the diagrams here what that is showing you. The usefulness then of an op amp operated in this manner is severely restricted and generally limited to comparator applications. With negative feedback, the overall closed loop voltage, okay, the ACL instead of the AOL, can be reduced and controlled so that the op amp can function as a linear amplifier. In addition to providing a controlled, Stable voltage gain. Negative feedback also provides for control of the unit, the input, output resistances, and amplifier bandwidth. The table below summarizes the general effects of negative feedback on op amp performance. So we can see here with and without negative feedback in terms of the gain, the input resistance, output resistance, and bandwidth. Configurations with negative feedback. An op amp can be connected in two basic ways using negative feedback to stabilize the gain. The extremely high open loop gain of an op amp creates an unstable situation because a small noise voltage on the input can be amplified to a point where the amplifier is driven out of its own linear region. We saw that on the graph. Also, unwanted oscillations can occur. In addition, the open loop gain parameter of an op amp can vary greatly from one device to the next. Negative feedback causes a portion of the output, takes a portion of the output and applies it back to the phase with the input, creating an effective reduction in gain. This closed loop gain then is usually much less than the open loop gain and independent of it. So some more terms here: closed loop gain, closed loop voltage gain, ACL. Closed loop voltage gain then is the voltage gain of an op amp with a negative feedback. The amplifier configuration consists of the op amp and an external feedback network that connects the output to the inverting input, like we just saw. The closed loop voltage gain then is then determined by the component values of the feedback network and can be precisely controlled by them. Again, hopefully in your lab you'll be able to configure a closed loop, open loop op amp and see these characteristics. In a non-inverting amplifier, we have an op amp connected in a closed loop configuration. The input signal is applied to the non-inverting positive input. A portion of the output is applied back to the inverting negative input through the feedback network. And we can see that non-inverting setup here, where we take the output and feed it back to the inverting input. This constitutes negative feedback. The feedback fraction, which uses the letter B, is determined by R sub F and R sub I, which form a voltage divider. Okay, and we can see that. We can see that back here. There's our voltage divider, R sub F, R sub I. The attenuation of the feedback network then is the portion of the output returned to the inverting input and determines the gain of the amplifier, as you see. This smaller feedback voltage V sub F then can be written as, okay, there's your voltage divider, and it equals B times V out. The differential voltage, V diff, between the op amp's input terminals is illustrated in 1820 below. So let's get that up here so you can see it. Okay, so there it is right here. You can see the differential input Vn minus Vf at the inverting and non-inverting inputs. So there's the relationship. This input differential voltage then is forced to be very small as a result of the negative feedback and the high open loop gain, A open loop. Therefore, a close approximation then is just Vn equal to or equivalent to V sub F. By substitution then, we can say Vn is equal to B V out. Rearranging then, we get V out by Vn. There's our typical ratio, and it's equal to 1 over B, or the inverse. The ratio of the output voltage to the input voltage is a closed loop gain. This result shows that the closed loop gain for a non-inverting amplifier, ACL, NI there, so you keep track of these subscripts, non-inverting, is approximately equal to V out over Vn, or 1 over B. The fraction of the output voltage V out then that is returned to the inverting input, okay, we can see that, is found by applying the voltage divider rule to the feedback network. So Vn is equivalent to B V out is equivalent to the voltage divider Ri by Rf. Rearranging then, we can get the ratio of V out over Vn as the sum over R1, which can be expressed as the gain, ACL, non-inverting, is equal to 1 plus RF over Ri. This equation shows that the closed loop voltage gain, ACL, non-inverting, of the non-inverting amplifier is not dependent on the op amp's open loop gain, but can be set by selecting values of Ri and R sub f. This equation is based on the assumption that the open loop gain is very high compared to the ratio of the feedback resistors, causing the input differential voltage, VDIF, to be very small. In nearly all practical circuits, this is an excellent assumption. So, example here, determine the closed loop voltage gain of the amplifier. So you can see we've got this configured just like we discussed. This is a non-inverting op amp configuration, therefore the closed loop voltage gain is ACL, non-inverting. We use the relationship 1 plus the voltage divider resistors R sub F over R sub I gives us a value of 22.3.